Okay, well, welcome. And today we are going to start a new chapter, chapter 18, which is on ionic equilibrium. So we still have, we're still going to be doing equilibrium for one more chapter. Okay, so hang in there with me, and we'll get through this. Before we get started, do you have any questions for me? All right. Don't see any questions, so I'll go ahead and get going. Good. All right. So I'll start this chapter by talking a little bit about antifreeze and how it's very dangerous, especially for pets. So if you have antifreeze in your garage and it spills, you want to make sure you clean that up really quickly because it turns out to be very dangerous for a dog or a cat who happens to lick it, and it could be, in fact, a deadly poison. Why is that? Well, remember, remember when we talked about hemoglobin, right? And we said that hemoglobin, right, picks up oxygen. I didn't give you the full equation at that point. I did include the role of acid in that equation, but this is the full equation, including the role of acid. So hemoglobin is protonated, it has a proton, and when it combines with oxygen, it forms HbO2 plus H+. And this is an equilibrium, right? So we know that according to the Chateliers principle, right, when the hemoglobin runs through the lungs where the oxygen concentration is high, it pushes it to the right, and the oxygen is picked up by hemoglobin, right? And then it flows through your body to your brain or to your muscles where oxygen is being used. The oxygen concentration is low, and this shifts it to the left, and hemoglobin unloads oxygen where it's needed, right? Now, notice that also in this system is H+, right? Which is the proton, right? Which means that this particular equation, this particular system is very pH sensitive, right? What would happen if you increased the acidity of the blood where hemoglobin does its job? What would happen to this equation?
It would shift to the left.
Shift to the left, right? If it shifts to the left, look what happens. You can't pick up oxygen. If you can't get oxygen to your brain and to your muscles, right, that's real big trouble, right? So it's very sensitive to pH, and that's why your blood is very highly buffered, okay? A buffer is a system that resists pH change. Okay, it's a system that resists pH change, and it's composed of an acid and its conjugate base, or a base and its conjugate acid. Okay, so in other words, it has significant amounts of both HA and A minus, right? An acid and its conjugate base, or B and BH plus, a base and its conjugate acid. All right, that's what a buffer is. It has significant amounts of both of these things. Taylor, do you have a question?
Yeah, just quick on the hemoglobin. Since your blood's a little bit basic, like it's not totally neutral, I think.
Yeah.
Is that why it pulls to pull oxygen, right? Like if you increase the acidity, it can't pull oxygen, but if you decrease the acidity,
well, it's just that your blood, the pH of blood is like 7 point, what is it? 7 point something, 7.39, I think, or something like that. And but the point is not exactly where it is. It's that this particular equilibrium is significantly changed by a change in pH, right? Right. Okay. So in other words, it's very sensitive to pH. If you change the pH, you'll change the position of this equilibrium and you'll affect the blood's ability to carry oxygen. Does that make sense?
So that's why it needs to be so heavily buffered.
Exactly.
It's really the change, not where it starts.
Right,
Or-
right. I mean, it is where it is, and this equilibrium and everything, you know, it's based on that. The trouble happens if the pH changes.
Okay.
Okay.
Thank you.
Yeah, so some of you have chimed in here, 7.39, 7.4 for the pH of blood. So it's almost exactly neutral, not quite, a tiny bit basic, but almost exactly neutral. Okay, so so how does that work, right? If you have an acid and the conjugate and a conjugate base, and I mean significant amounts of both, right? Because anytime you have an acid, you have a little bit of its conjugate base, right? Because as you know, an acid, right, ionizes like that. So you always have a little bit of conjugate base, but that's not what I'm talking about here. What I'm talking about here is significant amounts of both, right? So you'd have to intentionally make that. So for example, if you had a solution that was 0.100 molar in the weak acid HA and 0.100 molar in its conjugate base A minus, then that would be a buffer, right? It has significant amounts of both of those components. And by the way, you all know, right, that you don't just get anions like this on their own, right? So any kind of a conjugate base like this would be something like, you know, a salt, so NaA or whatever. It would have to have some counter ion, okay? But a lot of times the important part of this is not the counter ion, it's the conjugate base, okay? So how do buffers work? Well, if you have an acid and its conjugate base both present together, this can neutralize incoming acid or incoming base, right? The HA, the weak acid, will react with incoming base, and the A minus, or the conjugate base, will react with incoming acid, and it'll neutralize both of those, okay? Now, why is antifreeze so dangerous? Well, even though blood is buffered, there's a limit to how much incoming acid or base a buffer like this can neutralize, all right? And what happens is when antifreeze is consumed, which is primarily ethylene glycol, the liver converts it to glycolic acid. All right, and ethylene glycol is an alcohol. All right, so when the dog or cat starts to eat this ethylene glycol, right, it tastes kind of sweet, and it's also inebriating, right, because it's an alcohol, right? But then, so the dog initially starts to get a little bit inebriated, but then as the liver converts to the glycolic acid, at first the blood can handle it, right? Because the blood is designed to neutralize incoming acid or incoming base, right? Due to the buffering system in the blood, all right? But if the dog consumes too much of it, then the glycolic acid overwhelms the buffer, okay? And the pH of the blood changes, all right? And as you can see, it would become more acidic. And when it becomes more acidic, this goes up, and then the dog or cat would start to hyperventilate because it can't get enough oxygen. So it's trying to breathe heavier and heavier, right? And eventually, you know, if they continue to consume it, they can die because they won't get enough hemoglobin. I'm sorry, enough oxygen. Surprisingly, the treatment for this is to give the dog ethanol or vodka, right? And as weird as that sounds, what happens is the vodka, the ethanol and the vodka gets preferentially converted in the liver, and the ethylene glycol then is eliminated in the urine, right? So the vodka, of course, is going to get the dog hammered, but it's going to save its life, right? Because instead of the ethylene glycol being converted over to glycolic acid, you got ethanol being converted over to much less harmful products. Am I cutting in and out? Oh, I hate that. Okay. I don't know what to do. If anybody has a suggestion, if there's any techies out there that can help me with this problem, let me know. Is it worse here than it was in my other office? Oh, The treatment is, yeah, I'm hooked up directly to the Ethernet. Antifreeze, yeah, antifreeze is used in cars. It's so that the car doesn't overheat or it doesn't freeze in the winter. And what else? What was the other question? Oh, the treatment was to give the dog vodka, right? Because then the ethanol is preferentially converted in the liver instead of the glycolic acid, and the glycolic acid just is eliminated in the urine. So if you take your dog to the vet for poisoning due to antifreeze, they'll actually probably give them vodka. Okay. All right. Well, hopefully this internet problem will not persist too much longer, but we'll see. Keep me posted. Okay. All right. So what we're going to learn about then is buffers, right? And so buffers are the blood contains a buffer that maintains its pH at this very, very constant level, right? Very, very close to that number. All right. So here's an example of a buffer. Notice this buffer has acetic acid and sodium acetate, right? Significant amounts of both an acid and its conjugate base, okay? And so anytime you see that, you should think, aha, buffer, all right? Let's see. So how does a buffer work? All right, so now we have significant amounts of a weak acid and its conjugate base, all right? And they're in equilibrium with one another. So this equilibrium that we've grown to know and love, HA plus H2O in equilibrium with H3O plus A minus, right? We're used to situations so far where you only have an acid. So let's say you have 0.10 molar HA, right? We can calculate the pH of that. For a buffer, in addition to that, you have 0.10 molar, let's say A minus, right? So you have both of these things present at the same time, okay? So now what happens if you add, if you add acid to this buffer, right? What do you think it's going to react with? The acid or the base?
The base.
The base, okay? So remember the two equations I've given you already. This was one of them, right? And the other one's the equivalent equation for a base. Now I'm going to give you two more very important equations. And this is the first of those two. So we're going to call this equation number 3. Equation number 3. And it's not an equilibrium equation. It's a equation that shows how, wait a minute, what did I say? Oh, add H3O plus, sorry. So I'm going to call this equation number 4 because that's just the way I've numbered it in my notes.
Would you mind scooting the paper down a little bit?
Yeah, thank you.
Thank you.
The equation is this: A minus plus H3O plus goes to H2O plus HA. Okay, this is not an equilibrium equation. Notice I have a single arrow, not a double arrow. Okay, this is an acid-base neutralization equation. So remember way back last semester, we learned how acids and bases neutralize each other, right? So if I have some conjugate base and I add acid to it, they're going to react 100%, right? This reaction goes completely to the right, all right? And it's going to neutralize it. So in other words, this added H3O plus is going to react with the A minus, okay? Now, notice what happens. When the H3O plus reacts with the A minus, what does it form?
HA.
HA, right? It forms HA. So what that means is that the amount of HA is going to go up, right? So you form new HA. It's going to go over there and make the HA more, okay? So in other words, when a buffer absorbs some added acid, some of the conjugate base is converted to more of the acid, okay? Now let's see how this buffer neutralizes base, right? What do you think the base is going to react with?
The acid.
the acid. Okay, and that's equation number 3. So that equation is HA plus OH minus goes to H2O plus A minus. All right. So when this added base, right, reacts with the acid, you with me? What happens? It forms more of the conjugate base by this reaction, right? And so the amount of conjugate base goes up. Does that make sense? So that's how a buffer works. So I'm gonna write out all 4 of these equations for you right now. And these 4 equations, just make yourself a note card or a 3x5 card and put it up where you study, because these 4 equations are going to be the ones you're going to need in order to really understand this chapter. The first 2 you already know, right? The first equation is HA plus H2O in equilibrium with H3O plus A minus, right? That's an equilibrium equation, all right? You've seen that one. These are the 2 that I've been telling you are your best friends, right? This one and then the base one. Okay, these are both equilibrium equations. And when you work equilibrium problems, work in molarity and use an ice table, okay, for these 2 equations. The other 2 equations are neutralization equations. And the 2 I just gave you, I'm going to write them out one more time. It's the one for an acid, a weak acid be neutralized by a strong base. That's going to form H2O plus A minus. And the other one is a conjugate base neutralizing a added strong acid, and that's going to form H2O plus HA. Okay, these are not equilibrium equations. These go to completion. Okay, so these represent stoichiometry. You're just going to use stoichiometry on these. You're not going to solve an equilibrium problem. You're just going to use stoichiometry. I'm going to introduce a new kind of table for these that I call a BA table, before, addition, and after. Okay, so hang on to that idea. That'll be coming. And then for these problems, we're going to work in moles. Okay, we're going to work in moles. So these 4 equations, make yourself a flashcard, put those equations there, and you're going to use them over and over and over and over again in this material. Okay, so all right, so now let's see what happens in a buffer. All right, so in a buffer, here we have a solution that's not a buffer. This is just 0.1 molar acetic acid. How do we find the pH of a 0.1 molar acetic acid solution? What kind of problem do we work? If I just have the weak acid, acetic acid, 0.1 molar, how do I find the pH of that?
Ice table and equilibrium.
Correct. It's this equation. It's equation number 1. You'd make an ice table and you'd work an equilibrium problem. Okay. If you figured that out, you find the pH would be 2.9. Here is a solution of the weak conjugate base. Okay, 0.1 molar C2H3O2 minus. If you wanted to find the pH of this solution, how would you get it?
You would use the base equilibrium.
You use this equation, number 2, and you work an equilibrium problem again, right? With this being your initial concentration. Okay? Now, in this case, you have to find Kb for this conjugate base. How do you get Kb for that conjugate base? Do you remember?
10 to the negative 14th over Ka.
Correct. Ka times Kb is equal to 10 to the minus 14, right? So you can get Kb from Ka. All right, very, very good. Now, what if you have a solution that contains both? the acid and the conjugate base? Well, you still have to work an equilibrium problem, right? So let's just have a quick look at an example of that. Well, let's see. Do I want to do this one? No, let's do this. Let's do this one. So here's an example similar to this, where I have both of them, right? Weak acid, conjugate base, right? HF and F minus. Okay. How do I find the pH of that? Well, I work an equilibrium problem, right? Here's the reaction: HF plus H2O and H3O plus F minus, right? That's equation number 1 here, right? HF plus H2O, H3O plus F minus, okay? And this ice table has these switched around, unfortunately, but it's okay. You guys can figure that out, right? H3O is here and A minus is here, but it's the same thing, right? That's a neutralization reaction. So normally when we work a problem using this equation, it only has, let's say, the weak acid, and it doesn't have any of the conjugate base. In this case, I have acid and the base. So I need to include those both in the initial concentrations, right? So instead of having a 0 here, I have the concentration of the A minus, which in this case is F minus, inserted into the ice table, all right? And then, of course, this is going to go to the right. So this is going to be minus X, plus X, and plus X, right? And then you got 0.14 minus X. You just sum the columns, right? So far, this is just like working every other equilibrium problem we've ever seen, except that now, instead of just having the weak acid, you also have some amount of the conjugate base, right? So you set up the expression for K, right? You plug everything in. A minus is 0.071 plus X. H3O is X, and then the denominator HA is 0.14 minus X. Are you with me? All right, and then you find Ka, and you solve that. You can make the X a small approximation, right? Because Ka is pretty small. And by the way, having the conjugate base here makes the X a small approximation even more likely. Why is that? If you didn't have the conjugate base, this would go further to the right, correct? But because I have some of that conjugate base, that pushes it to the left and doesn't go as far to the right as it would normally go. So the X is small approximation is even more valid in buffers than in just pure acid or pure base. All right. So you make the X a small approximation. You solve that for X, and you get that X is equal to 1.4 times 10 to the minus 3 molar, right? We can check the X a small approximation, and we find that it's fine, right? It's equal to 1%. So we're good on that. My computer tells me when the internet is unstable, so I think I might just pause and then see if that, yeah, okay. All right, yeah, so I will, whenever I see that message, I'll just repeat what I said. So if I seem a little repetitive, that's why, all right? But what's happening here is that I plug into the expression for K, right? F minus H3O plus over HF. I make the X a small approximation. And then I solve for X. And then X is, of course, equal to H3O plus concentration. So I can, before I do that, though, this is just checking that the X a small approximation is valid. And it is, right? And so I get that X equal to 1.4 times 10 to the minus 3. And so then from there, I'm not going to worry about those things. I can get that the H3O plus concentration is that, and then I get my pH is equal to 2.85. Okay. Does that make sense? All right. Now, that's kind of a little bit of a long procedure. You have to work through an equilibrium problem. All I did here on the last slide is I found the pH, which is minus the log of what I got for X, right? So this is just like many of the equilibrium problems we did before. Don't worry about this stuff here. Just worry about this in blue. This is the H3O plus concentration, which is equal to X. Okay. Checking the X's small approximation is here, right? Remember, I just compared the number to what I subtracted it from, which was 0.1, which was 0.14, right? And that gives me 1%. We use this equation right here. Okay, stick with me here for a minute because it turns out that we're not going to have to do all this every time because there's a good shortcut. Okay, it's a really good shortcut for these kinds of problems. All right, and that shortcut is called the Henderson-Hasselbalch equation. And so I'm just going to call it the HH equation. And it says that the pH and this applies to buffer, right? Buffer. So you have to recognize a buffer. How are you going to recognize a buffer? Significant amounts of an acid in the conjugate base or a base in its conjugate acid, right? Once you see both of those things, you go, tick, ting, ding, 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 buffer. So then you're going to use the buffer equation, which is going to give you the pH directly. Sorry, the Henderson-Hasselbalch equation. And the equation is this: pH is equal to pKa plus log of the concentration of the base divided by the concentration of the acid. Okay. So let's do that same problem again that we just did, but now let's do it using this equation. Okay. pKa, do you remember what pKa is? Who could tell me?
Is that the acid ionization constant?
Ka is the acid ionization constant. What's pKa?
For a gas.
The negative log of that?
Correct. Minus the log of Ka. Remember that? pH is equal to minus the pKa. P anything is minus the log of that thing. Okay? pH is minus the log of the H plus concentration. pOH is minus the log of the OH minus concentration. pKa is minus the log of Ka. pKb is minus the log of Kb. And whatever. Whatever is minus the log of whatever. Okay? So this little handy equation right here does the very same thing that we just did in that equilibrium calculation, but it just condenses it down to one equation. Okay? So for example, if we want to use the equation to calculate the pH of the buffer that we just did that, we would just go, easy. pH is equal to pKa, 3.15, plus the log of the base. Which is the base here, the HF or the KF? Which is the
KF.
The KF, right? Potassium fluoride, because F minus is the conjugate base, right? So it would be 0.071 over 0.14, right? And if I work that out, I get 2.86, which is the same thing we got from doing all that work earlier, right? So what do you rather do? Work an equilibrium problem and do all this stuff, or just solve into that equation, plug into that equation?
Equilibrium for sure.
Smart Alec. Okay. All right. How about you try this? Use the Henderson-Hasselbalch equation and find the pH of this buffer. Oh, let me start the poll. Almost forgot. Okay, try to answer in the next 10 or 15 seconds. Okay, this is really fabulous. Fabulous, fabulous, fabulous. The correct answer is A, and look at that. Almost everybody got it. So awesome, awesome, awesome. Great job. Thank you. You can see, right, that if you plug into this equation, I saw that my internet just got shaky again. Can you hear me again? Okay. You just got to plug into this equation. So pH is equal to pKa. So that's minus the log of 4.1 times 10 to the minus 3, right? Which is equal to 2.39, right? Sorry, that's pKa, right? And then pH is equal to pKa plus the log of the concentration of the base divided by the concentration of the acid, right? So that's equal to 2.39 plus the log, which is the base component. That's all you got to figure. Two things you got to figure out here. First of all, you got to go, this is a buffer, right? How do you know it's a buffer? Acid and its conjugate base, okay? And in this case, the concentrations are the same. So it's 0.500 molar divided by 0.500 molar. That's equal to 2.39 plus the log of 1. What's the log of 1?
0.
0. So this is equal to 2.39. Okay. So notice, it's really nice. When the two buffer components are equal, right? Then pH is just equal to pKa every time. Okay, according to the Henderson-Hasselbalch equation. So you can solve those kinds of problems really quickly. Okay, does that make sense? So what we should be able to do now is say, aha, I see you, buffer, and I know how to calculate your pH, right? How do you recognize a buffer? An acid and its conjugate base, right? Like here, acid, conjugate base, or here, acid, conjugate base, right? Or this problem that we did, this problem that I showed you at the very beginning, here, acid, conjugate base, okay? Whenever you see one of those, this is your equation, right? Henderson-Hasselbalch equation. You just directly calculate the pH. It's the equivalent of working an equilibrium problem, all right? But you don't have to work the equilibrium problem. All right. Sorry. Okay. Now, the next thing we want to be able to do is to calculate how the pH changes when I add acid or base to a buffer. Okay? I want to figure out how the pH changes when I add acid or base to a buffer. These four equations, again, keep them with you at all times, right? Keep them in your front pocket. Be ready to use them at a moment's notice, right? Because we'll be using them a lot, okay? And I'll show you how to use these two right now. These two we've already been using all along. Now I'm going to show you how to use these two. So here's what we want to do. Let's suppose we have 1 liter buffer. So we have 1 liter of a buffer that is 0.100 molar in the generic acid HA and 0.100 molar in the generic conjugate base A minus. Okay. And we want to find the pH. Right. And we want to find the pH after find pH initially, and then after adding 0.025 moles of H plus, and then also after adding 0.025 moles of OH minus. All right. So what we want to we want to know how to deal with all those situations. So pH, the pH of this buffer, Who can tell me right away, what is the pH? It's going to be equal to what?
pKa.
pKa.
pKa, right? pH is equal to pKa. So number one, pH is equal to pKa. Why? Because you have exactly equal amounts of both of these things. When you plug them into the Henderson-Hasselbalch equation, you're going to get the log of 1, which is 0, which means pH equals pKa, yeah? All right, number 2, after adding 0.025 moles, so add 0.025 moles of H+. Okay, sorry, I cut out again. Add 0.025 moles of H+.
Sorry, one question.
Sorry, yeah.
If it doesn't state that pKa, do we just say it's equal to pKa? We would see that from a graph or something like that?
Yeah, you'd have to know pKa to actually find a value, but I'm just showing you kind of a generic problem here. So whatever pKa is, pH would just equal that for this buffer, this generic buffer. Does that make sense? But yeah, you'd have to be given pKa to give you to get an exact value. Okay, so again, what happens when I add H+? Well, again, remember this, right? If I add H+, same thing, that's same thing as H3O+, what does it react with?
You get HA.
What does it react with?
Oh, sorry. It
A
reacts with the base.
Reacts with A
Base.
minus, right? So of my 4 equations here, which one do I want to use?
Number 4.
Number 4, correct. Okay. Now, let me back up for a minute. These kinds of problems are going to have 2 parts. A stoichiometry calculation, which is going to be one of these 2 equations, and then an equilibrium calculation, which you can do using one of these 2 equations, or you can use the Henderson-Hasselbalch equation, which is a lot faster. We'll use the Henderson-Hasselbalch equation for the second part, okay? So we know that it's going to react with A minus, and we know that we're going to use equation number 4. So let's write that equation. We got A minus plus H3O plus, right? And what does that form? H2O plus the conjugate acid. Okay, now that's this equation right here. Remember, this is stoichiometry. The kind of table we make is what I call a BA table, and it's going to be this. I'm going to say before, sorry, let me write that out. Before, and then and I'm going to keep track of my addition, and then I'm going to have after. So that's why I'm calling it a BA table, before, addition, and after, okay? So what's my A minus concentration? Before I add anything, well, it was given
0.100.
0.100, exactly correct, okay? What was my H3O plus concentration before I add anything? It's essentially
Roughly 0.
close to 0, correct? And then this is the HA concentration is 0.100 molar, right? Because I have a buffer that has both of those, okay? Now I'm adding 0.025 moles of H+. So my addition is 0.025 moles of H+. Now don't confuse this with an equilibrium table. In an equilibrium table or an ice table, right, I'm summing the columns. Here I'm not summing the columns, all right? I'm figuring out the stoichiometry of the reaction. These are going to react 100% with each other, right? So in other words, I have 0.025 moles of this and I have 0.1 moles of this. That means that all of this is going to be consumed, and this is going to come down to 0.075. okay? Because it completely neutralizes. This is going to go down to about 0. We know it's not exactly 0 because that's the thing we're trying to calculate ultimately, right? And then what's going to happen to the conjugate base? So let's see what happens here. Let's go back. Let's go back here. Here I added H3O plus, reacts with A minus. It lowers the amount of A minus, right? But then what does it do to the amount of HA?
It makes HA.
It makes HA bigger, right? So how much HA am I going to have after my addition?
0.125.
Correct. 0.125. All right. So that's the first part of my calculation. The second part of my calculation is to do an equilibrium problem using the Henderson-Hasselbalch equation. So then I'm just going to go pH is equal to pKa plus the log of base over acid, except now the amount of base and acid have changed, right? They're no longer 0.1 and 0.1. What are they now?
0.075 and 0.125.
Correct. The base is 0.075 and this is 1.2, 0.125. All right, so that's pKa. That's equal to pKa plus the log of 0.600. Now, one thing about logs, remember the log of 1 is 0. The log of a number greater than 1 is positive. The log of a number less than 1 is negative, right? So that's equal to pKa minus 0.22. Okay, so if you know pKa, you just subtract 0.22 and that gives you the pH. All right, does that make sense? I see a question from Emily.
So, because we're working in molarity and moles here, it seems like it's made simple because we have
I made
one
it easy.
liter. We have 1 liter. So in an equation in which we had more or less than 1 liter, that would complicate this problem quite a lot, right?
A little bit. All you'd have to do, let's say we had, instead of 1 liter, let's say we had 0.5 liters. What would change? You'd have to figure out the number of moles because Baugh table is always going to be in moles, not molarity. Okay. In this case, I had 1 liter just to keep it simple. But let's say it was 0.5 liters. Then I'd go, okay, 0.5 liters times 0.100 moles per liter would give me 0.500 moles. Oh, sorry, 0.0500 moles, right? So if I didn't have exactly 1 liter, I would just have to figure out the moles.
And then we would use that in place of our 0.100 molarity.
Correct.
Okay.
Correct. So always, and again, we're going to go here. Sorry, I should have pointed that out, Emily. So thank you for asking. That was my mistake. Whenever you're working with these equations, you always want to work in moles. So what I should have said is I said, oh, okay, we have 1 liter, 0.1 moles per liter. Therefore, we have 0.1 moles. These are all moles, not molarity, right? And now, oh, and one other thing, when you substitute back into here, this is concentration, not moles. But the two components are in the same solution, right? So if you divide by liters, the liters are going to be the same. So the nice thing about the Henderson-Hasselbalch equation is you can work in moles or molarity either way, and it doesn't matter. All right. So if we go back to here, our 4 equations, these two, you're always going to work in what?
Molarity.
Molarity. These two, you're always going to work in
Moles.
Moles.
Henderson-Hasselbalch equation,
Either.
Or
either one. Okay? All right, very good. Now, let's do the second part of this problem. What happens when I add 0.025 moles of OH? Oh, this was, oh no, sorry. The second part was this, add 0.025 moles of OH minus. Okay, so that was adding H plus. Now we'll go to 3 pH after adding 0.025 moles of OH minus. Okay, now, what happens when I add OH minus? What does it react with?
Reacts with the acid.
Correct, it reacts with the acid. So which equation do I want in that case?
You want number 4.
Three.
Number
Three.
what?
Number 4.
Number 4, correct, right? Because I have I'm adding, not number 4, sorry. I'm adding OH minus, right? What's the OH minus we're reacting with?
HA.
The acid.
HA. So which equation do I want?
Three.
Three.
Number 3. Okay, I want equation number 3. So I'm going to write that equation down. A minus plus H3O plus goes to H2O plus HA. This is going to be a bar table. Okay.
Sorry, shouldn't it be the HA plus OH minus equation?
Thank you. Why did I do that? HA plus OH minus goes to H2O plus A minus. That's the correct equation. Thank you. All right, so again, we're going to use these same values. 1 liter times 0.1 moles per liter is how many moles of HA?
0.100.
0.100 moles of HA, about 0 of that. How many moles of A minus? 1 liter, 0.1 mole per liter. 0.100 moles of that, right? Now I'm going to add the 0.025 moles of OH minus, right? I added it. Notice what happens. I form A minus, right? So what happens to the amount of HA?
It decreases.
It decreases to 0.07,
0.075.
0.075, and the amount of HA, sorry, the amount of A minus
Increases.
0.125.
increases to 0.125. All right, then pH is equal to pKa plus the log of, in this case, the base is 0.125. The acid is 0.100, right? And that becomes pKa plus 0.22.
Wait,
Okay,
Why would it?
why is
not-
it 100?
Yeah, wouldn't it be 0.075?
Oh, thank you. Thank you. Thank you. Thank you. What did I do wrong? Point. Oh, man. .075, right? The acid, yeah, 0.075, 0.125 or 0.075. Correct. Yes, my bad. I was thinking ahead too much. So here's what happens. Notice what happens. When I added acid to my buffer, what happened to the pH?
Decreased.
It decreased. Decreased, right? Does that make
Yeah.
sense? If I add acid to something, it should become more acidic, right? And in fact, it does. But it only decreases by a small amount, right? If this wasn't a buffer, the pH would drop by much, much more than that, okay? Similarly, when I added base to my buffer, what happened to the pH?
It goes up.
It goes up by a little bit, right? Just kind of like you'd expect. So think about this as you're working through these problems. If you add acid to a buffer, you expect the pH to go up, to go down a little bit. If you add base, you expect the pH to go up a little bit, okay? All right. Let's do another example here. And we're going to compare what happens when you add sodium hydroxide to a buffer compared to adding the same amount of sodium hydroxide to pure water. Okay. So if you think about this buffer, okay, it's 0.1 molar acetic acid and 0.1 molar sodium acetate. pKa is 4.75, right? So what's the initial pH of this buffer before I add the base to it?
Is it just 4 point?
Correct.
or
4.75, right? 4.745, right? That's the pH because they're equal components. When I add this small amount of hydroxide, right, and I do a Baugh table, I find the pH is equal to 4.75 plus the log of 0.110 over 0.090. So the pH jumps from 4.745 to 4.83, right? This is a problem just like the one we just did, right? But what happens if I add 0.010 moles of base to a liter of pure water? Well, the OH minus is 2 and the pH is 12. All right, so what I just do, if I add the OH minus to a buffer, the pH goes from 4.7 to 4.8. If I add the same amount of OH minus to pure water, the pH goes from, well, what's the pH of pure water?
7.
7 to 12. You see the difference? Okay. You add OH minus to pure water, the pH goes from 7 to 12. You add the same amount of OH minus to this buffer, it goes from 4.7 to 4.8. That's what a buffer does. Okay. It does change pH a little bit, but it's very small compared to what it would be otherwise. Okay. I see some questions. Sophia.
For the Henderson-Hasselbalch equation to work, you said there the excess-small approximation had to work.
Correct.
How can we check do we check the same way?
You know what? I'm not gonna, yeah, you would check the same way, but I'm just going to tell you right now, I'm not going to give you any buffer problems for which the excess-small approximation does not work. Okay. So anytime you see a buffer in this class, you can assume excess-small works and you can get Am I back? Anytime,
thank you.
Anytime you see a buffer in this class, you can assume that the excess-small approximation will work, which means you can use the Henderson-Hasselbalch equation for every single problem you solve. Okay? The 090 here came from setting up a Baugh table for that same reaction, kind of like we did here. But I just skipped over because I didn't want to do the whole problem again, right? But that's where it comes from. In other words, when I add NaOH, right, I had 0.010 moles, so I increased the amount of A minus by 0.010 moles, and I decreased the amount of HA by 0.010 moles. Okay? This is just kind of to show you the difference. Okay. Let's see if this is making sense. Let's see where we are. So go ahead and try to answer this question. let me give you a little bit of a hint here in case you're struggling. So you have a buffer that's HF and NaF, right? Now you're going to add HCl, right? Which buffer component, this is an acid, right? Which buffer component is it going to react with? The acid or the base?
The base.
The base. It's going to react with the base, right? So if it reacts with the base, which equation is it? 3 or 4?
4.
4, right? So if it's equation 4, what happens to the concentration of the conjugate base?
Decreases?
Decreases, right? If you have the acid reacting with the conjugate base will decrease, and what will happen to the concentration of the HF?
It will increase.
It'll increase, right? So the right answer is D, right? F minus will decrease. Again, the way you think about that, you said, okay, I'm adding acid. I have a buffer. Which component is it going to react with? Does the acid react with the acid or does the acid react with the base? It reacts with the base. And then you think, okay, which of these 4 equations shows the neutralization of a base with an acid, right? And in this case, here's your base, and that's your acid that you're adding, and that's the reaction. That's the way you want to think about this, okay? And I'm going to end the polling there. Most of you got, a few of you got it backwards. But again, the way to think about this is to think, okay, I'm adding HCl. What does it react with? The conjugate base. So therefore, this gets neutralized. This goes down, this goes up, okay? All right, try working a problem here. Just like the one we did. Again, we're going to do 1 liter here, so you don't have to calculate the moles. It's super straightforward in that respect. But now I want you to calculate the pH when you add 0.022 moles of HCl to the solution. Okay, go ahead and try that. Just a quick hint in case you're struggling, right? You're adding strong acid. This is your buffer, acid and the conjugate base. The strong acid is going to react with which one? The weak acid or the conjugate base?
Conjugate base.
It's going to react with the conjugate base, right? So if you're looking at these equations, right, which equation is it?
4.
4.
Number 4.
Equation number 4. Okay. So it's equation number 4. So you'd write A minus plus H3O plus goes to H2O plus HA. And you'd set yourself up a bar table, right? Like that. And remember to always work in moles here, but again, you have 1 liter. I'm keeping the numbers simple, right? So what are the number of moles of A minus?
0.1.
0.1 and HA
0.10.
0.1 as well, right? So you have the same amount of both. Yeah, well, that's okay. I just had another significant figure here. And then you're going to add H3O plus, right? So that means this is going to go which direction, up or down?
It's going to go down.
Yeah.
Down 0.078. This is going to go up to 1.22, right? And then pH is going to be equal to
0.122.
0.122. Thank you. pH is going to be equal to 4.25 plus the log. And again, at Henderson-Hasselbalch, you can work in moles or molarity, right? How many moles of base do I have?
Zero 0.078.
Correct, 0.078. And then the acid is that, right? So my pH is 4.25 minus 0.194, which is equal to 4.06. Notice I added acid, and in which direction did the pH go? It got more negative, more acidic, right? So that makes sense, okay? So the right answer was A, and most of you got that, so nice work. All right, very good. Okay, there's a couple questions here I've been ignoring, I'm sorry. Minerva.
My question was in regard to the example we did together. I just wanted to make sure that I got what you said right. It was for adding 0.025 mole of H plus, and then the same for adding the same amount of OH minus.
Oh, so wait. No, yeah, okay, yeah.
Yeah, so when you add more acid, the pH decreases, and when you add more of the base, the pH increases.
Correct. Yep,
Okay, that was it. Thank you.
yep. Ryland?
I'm just trying to interpret these equations we've got. I mean, is it just as simple as equation 4 shows us adding acid so to a base? So if it says add an acid, then that's the one I use. And equation 3 shows us adding base to an acid, and so if it says add a base, that's the one I use.
Correct.
Okay.
Yep. Good. Any other questions?
Can I just ask one clarifying question about
Yes.
that problem we did?
Yeah.
So we get our base goes to 0.078 because we're adding acid, so that's neutralizing, which makes it less. Is that right? And then our acid in our chart goes to 0.122 because adding a strong acid to the weak acid makes it more acidic, or how do we think about that, of which one decreases and which one increases?
Are you asking about this problem?
Yeah.
Yeah. So the way to think about it is you first look at the problem. You say, okay, and this is the deal with all of these problems now. Like a lot of them look kind of similar, right? Like, you were adding acids to bases. We're working weak acid equilibrium problems. So you got to get familiar with kind of what is the beast you're trying to slay, right? What is the problem you're trying to solve here? Okay. And so, we've seen find the pH of a weak acid, right? When you're asked to find the pH of a weak acid, you got to go, oh, okay, that's an equilibrium problem. And I use this equation, right? When you see find the pH of a weak base, you got to go, oh, okay, that's an equilibrium problem. And I work this equation, right? And I use ice tables. And I always work in molar, all right? Then you might have problems where you say, okay, find the pH of a solution that is 0.1 molar HA and 0.1 molar A minus, right? And then you got to recognize that. You got to say, oh my gosh, significant amounts of an acid and its conjugate base. Ding, 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 ding. That's a buffer. How do I solve buffer problems? Henderson-Hasselbalch equation, right? I plug into the Henderson-Hasselbalch equation. And then these problems are, okay, I have a buffer, but in addition, I just broke up, so I stopped for a minute, and I'm going to repeat myself. I have a buffer, but in addition to that buffer, I'm adding acid or base to a buffer, right? And then what you got to say is, okay, if I'm adding acid, I got to think about it. What does the strong acid react with? The base or the acid? Well, strong acid will always react with the base, right? With the conjugate base. So there's my conjugate base neutralizing incoming added acid. And now, since it's one of these two equations, I know it's a Ba table, not an ice table, right? Does that answer your question? Now I forgot your question.
It does. So for that problem specifically, the figures we end up with are 0.078 and 0.122. And I'm just wondering if you could go over why we're subtracting from the base and adding to the acid.
Perfect, perfect. So you'll set up your problem like this, right? You'll use this equation, right? In this case, it's this one, right? And then you put in before your addition, you have equal amounts of both. And then you got to go back and think about what happens when I add an acid to a buffer. So let's go back to that real quick. Here's my buffer, right? Acid conjugate base. Okay. I add acid. What's the acid going to do? It's going to react with the conjugate base. So what's going to happen to the amount of conjugate base? It's going to go down. By how much? By exactly the stoichiometric amount of acid that I added.
Is that because it's kind of neutralizing it?
Correct. Yes.
Okay.
It's undergoing this equation. So remember back when we were looking at like limiting reactant problems, right? If I have 1 mole of this and 0.25 moles of this, right? This is the limiting reactant. So I have that gets completely used up, and I have 0.75 moles of left of this. That's exactly what we're doing here, right? Except in this case, it's 0.022 and 0.1, right? So this gets completely used up. So that goes to about 0. This goes to 0.078 because it neutralizes, it gets used up in neutralizing all of that, right? But then notice I've formed new HA. How much? The exact stoichiometric amount, 0.022 moles. So that's why I add 0.22 moles to that, and that becomes 0.122. And the amount of HA.
And that's because adding an acid to another acid is just making it more acidic.
I wouldn't think about it that way. I would think about it.
Okay.
You've already thought about the idea that you added acid and the acid reacts with the conjugate base. The result of that reaction is more of the acid. That's a better way to think about it, I think.
Okay, got it. Thank you for clarifying.
Yeah, yeah. Okay, so let's see, where are we? All right, what if I have, let me just do this last topic and then we'll be done for today. what if I have a buffer that's now composed of a weak base and its conjugate acid? So a buffer that's composed of a weak base like ammonia and ammonium chloride, right? So this is a buffer that is NH3, NH4 plus, right? If I have significant amounts of both, that's also a buffer. The way to solve these problems is just like you solve any other problem. Once you recognize as a buffer, what equation are you going to use? Henderson-Hasselbalch equation, right? You're going to use that equation. Now, the only tricky thing is here, of course, you got to recognize that this is the base, right? So that's the concentration you put there. That's the acid, that's the concentration you put there. And this is pKa, not pKb. So just like when we were trying to solve problems for weak bases and figuring out their pH, we have to figure out pKa for this acid, right? And what you have to remember is we already know that Ka times Kb is equal to 10 to the minus 14. It's also the case that pKa plus pKb is equal to 14. All right. So if you know one, you know the other. Right. So that's the only thing. Just make sure you always use pKa for whatever the component of the buffer is. That's the acid. All right. If you're given the Ka for the base, then figure out Kb and then figure out pKb. If you're given pKa for the acid, then just use this equation and get pKb. Okay, so let's do a quick example here. What's a pH of a buffer that's 0.5 molar? So 0.50 molar ammonia and 0.2 molar ammonium chloride. All right, and they're giving us pKb is equal to 4.75. When you read this problem, you should think, aha, I have a base and its conjugate acid. I have significant amounts of both, right? 0.5 molar and 0.2 molar. So aha, I have a buffer. So I think Henderson-Hasselbalch equation. Right, I think Henderson-Hasselbalch equation. So then what's the concentration of my base? Which is the base?
So
0.5.
0.5. What's the concentration of my acid?
0.20.
0.20, 0.20. And then what's my pKa? Oh, wait, I'm not giving pKa, I'm giving pKb, but that's okay. pKa plus pKb is equal to 14, right? So pKa is equal to 14 minus pKb. That's equal to 14 minus 4.75, right? That's equal to, what is it?
9.25.
0.75.
Thank you.
Oh, 9.25, sorry.
9 points. Where's my problem? Did I not?
It's 9.25.
Thank you. I know, I was just trying to find my final answer here. 9.25, and thought I had this worked out, but maybe I don't. Ah, here we go.
I have the answer.
I think it's
Final.
It's 9.25 plus what, 0.4? Is that correct?
Yeah, your final's 9.647. Goes on for a while.
Perfect, 9.65, okay? So that's how you do a buffer that's composed of a base and its conjugate acid. All right, very good. Oh, that's why I didn't have it worked out, because I worked it out on here. I'm losing my mind. All right, very good. All right, next time we'll look at buffer range and buffer capacity. Thanks everyone for your attention. I really appreciate it. Of course, I'm going to stay here and answer any of the questions that remain. So please stay on the line if you have questions. Otherwise, have a great afternoon. Enjoy the beautiful weather. I'll see you on Wednesday. Thank you.